what is the maximum information that you can get from one way? If the answers are equiprobable. You know, we saw that the maximum information is for uniform distribution. So uniform distribution on the balance has to be 3 possible answers, right? This is heavier, this is lighter, and the same. So there are 3 possible answers. So we really want to have the coins distributed in the 2 plates in a way that it's approximately uniform, you know, to get the most. Like if you, for example, if you put 6 coins in one plate and 6 in the other, of course there's a chance that there will be no counterfeit and then they'll be the same, but that chance is small with respect to the 2 other ones, and then you cannot proceed in getting the answer in 2 more ways. So you really have to, the initial weighing, of course, will be 4 and 4 and 4 on the side, okay? Because then you more or less distribute the probabilities. And then you can go on and try to get the solution. But as I said, there is an interesting solution that's based on a ternary Hamming code that I suggest that you also investigate. Okay, with that, let's go on. We talked about source coding. We also, there is something that, there was a comment last time, and I included the information here on the, when we go for the entropy rate of random processes, there was a comment about the condition, I mean, what are the conditions on the process, and they have to be stationary, okay? So this is for stationary processes, as it's stated here. And for stationary processes, these limits exist, both of them, and they are equal, okay? Okay, so we actually went on. Somebody also asked me to restart at the theorem here. So here's the theorem. Yeah?
Ask a question about the weighting problem.
Okay.
You said that we know that if we put 4 and 4 and 4 aside in the first weighting, it's like kind of equal from all
Yeah.
thing that we had.
Yeah.
Might be entropy.
Yeah.
But we know that entropy is the average information.
That's true.
I was wondering if there is any proof that this way we can achieve the minimum number of weightings that we want. Is there any?
That you have to start with 4, 4, 4?
No, I mean, you start with 4, 4, 4 and go on to the next step. You can again do the same thing.
Yes, yeah, you can still put 4, 4, 4 because you already know about some of them. You can use them as ballast, you know, because you know that they would be legitimate from the first weight.
But we can again use a similar approach to maximize the average information. Or
That's true. I think that is the idea. You really want to have maximizing the amount of information that you get. And for example, how many questions are you to answer? I mean, how many answers are you to have at the end? Well, 24 plus 1, because there is the no counterfeit and the 24 identities plus, you know, the 12 plus heavier or lighter. So there's 25 solutions possible. And with 3 weighings, you have 27 possibilities. So it doesn't have a lot of margin, you know, it's cutting very close. But if you had a situation when you have, for example, 29 answers, you only have 27 possibilities. There's no way you could get that, okay? So.
Is there any study about that related to entropy?
I don't know. I think it's possible that this could be actually explored into something deeper. But I think it's you know, it's something that highlights the need to maximize entropy at each step of the way. Yeah. We can talk more about it. Okay, so the first theorem of Shannon basically states that the average, the expected length of a code, of an instantaneous code, has to satisfy this bound. In other words, has to be greater or equal to the entropy of the source. Okay, and this is an efficient code that gets within 1 of the entropy, which is nice, but it's not the optimal one. The optimal one was actually found by Huffman, and Valdemar was telling me yesterday that this was, Huffman was a student at MIT, and this was actually a homework that he took home, and you know, I guess maybe it took him a couple of of days or so, and he came up with a solution that gave him instant fame. You know, it's the optimal solution. And I think the best way to describe it is to show an example, because, you know, it's a little bit involved. Basically, you just put the probabilities here in decreasing order, and then you combine. If you have a binary alphabet, you combine every 2. Here's Voldemar. Yeah, didn't notice that you were here. So you combine every 2, you add that, and now you do the new order of the probabilities, always in decreasing order. And you associate a 0 and a 1 with this 2 here, okay? So as indicated here. Then you do the same thing with the second list. Now it's 0.45, it goes up there. And then you have until you get 1. Now you can get the code. For example, by looking at it in reverse order. For example, this one here, it's easier to construct it in the reverse order here. This one has a red here, okay, which is a 1 there in the last position. And then nothing is done with that 0.3. But now it has a 0 and then again a 0. So it's going to be 1, 0, 0, and so on. So you construct that. And this one has an average of 2.3 bits per source symbol. And it is the minimum length that you can get with a code, with an instantaneous code. Okay. So there are some other efficient codes, and some of them are interesting because they tend to learn what is the distribution of the source. One of the problems with Huffman code, suppose you now want to have a Huffman code for not just one of these axes, but 2 of these axes, like have 1, 1, 1, 2, 1, 3, 1, 5, and then 2, 1, and so forth. Well, you cannot get that from this. It's not something you can just adapt. You have to start fresh with the new probabilities. So there is this aspect of the Huffman code made it, in many situations, not the most practical code. So there are some other codes, like arithmetic codes I mentioned recently, the guy who was visiting at Stanford, you know, talking about this code. He was working for IBM, and this became a very important code commercially. Of course, it was sometimes not used because there was a proprietary issue. You know, it had to pay royalties to IBM. Now it's over because it's past 30 years, so it's now a public domain. The only problem that I think, you know, in many applications, it's the best code because it learns the distribution of the source. It's adaptive. You know, it's something that can be done recursively. So it's very interesting. The only problem is it's extremely complicated. You know, it's not a simple code to implement. You know, there is some issues. You have the Q coder, which is one type of implementation by IBM. Another by the way, arithmetic codes are basically an evolution of this set of codes here, Shannon-Fano Elias code. And then Lempel-Ziv codes are very interesting. They are very much used for text. They learn the distribution as well. They built a dictionary. You know, they are in the zip program and also in the compress. And typically they get some very good performance, compression rates of about 2 or 3, depending on the file. But there is one that I'd like to present to you because it has this characteristic here. It's extremely simple. It's really simple. And that's the Golomb codes applied together with run-length codes. Okay, so I'll have a little example here. And they also have very good performance. They don't beat the other ones, but they get, you know, like within a very good distance. Run-length codes are used to encode long binary sequences of zeros. Suppose you have some type of source that has a long sequence of zeros, okay? And the higher this probability of zeros, the better in terms of the performance of the code. So zeros are much more likely than ones, or vice versa. Of course, it doesn't have to be like that, so you can input. So the initial step is just to get a run-length code to encode these long runs. And we represent the 0 runs as integers. For example, suppose this is the input. Then we have a run of 5 here. Then there is a 1. We don't need to represent the 1 because that's just the separation here. Then there is a run of 6. And then one of 3 and 11 and 2 and so on. Okay? Now we use a Golomb code to represent this sequence of integers. Okay? By the way, it's nice to have the code represented by finite runs, I mean complete runs. So if there is not a 1 here, we put a 1 there, okay? Just to make sure that there will be a complete run. Okay, now what we do is we do a variable length code for the integers, and we choose an order m. The m is important. It has to be tuned to the source, to the probability of the source. And if it's not, then the performance is not going to be as good. But if it's well tuned, and we'll see how we tune that, we can represent each integer n by just the quotient of the division by m plus the remainder, okay? Now the quotient, what we do with it, we use a unary code. A unary code is just a number of ones, the same number that is q. And we use a comma. We're going to introduce a comma, a 0 comma. And of course, one may look at some ways of trying to get rid of this comma here, because of course that's a little bit of an overhead. And then we use a prefix code, and there's some work that shows that this type of prefix code is the Huffman code for integers that are distributed geometrically. So there is, one way you usually have a tree code like that, and you associate the longer numbers with the with these trees on one particular side. So you have 0, 1, 2, 3, 4 for an example with m equals 5. So these numbers here are then used to represent, this code here that's represented here, it's used to represent the R, the remainder. Okay, so 0 would be a 0, 0 coming from this tree. 4, for example, 4 would be a 1, 1, 1. Okay, that's represented there. Okay, now we just put the Q, the comma, and the R. The Q, the comma, and the R for each one of these. So we do that. Let's do that for the example. The example is here, 5, 6, just as before. So divide by 5, we're using it m equals 5. So there is a quotient of 1 with a remainder 0, and then a quotient of 1 with a remainder 1, and so on. With the 11 here is going to give you a quotient of 2 with a remainder 1. And then we have this these sequences here. This is the representative for Q, that's the comma, and then the representative for R. Similarly, in some cases the Q is 0, so you just don't have it. You just put 0 once, which is nothing. So in this case here, for example, Q is 0, so you don't have anything for Q, you just put the comma, all right? And then you have the 1, 0, all right. So the original length was 32, the output length in this case is 20, and there is some compression. Typically, you can get access rates of about 1% with respect to the entropy. So it's a very simple, simple code. And the idea to get the M is you want to have the probability of the output being close to an uncompressible sequence, which is a sequence of zeros, ones with probability 1/2. So we want to have that run that gives about 0.5 probability be the number necessary to generate the M. So you try to solve this equation here, the approximate equation. I didn't raise this to the exponent here, but it's P to the M should be close to 1/2. And then when you invert that, M is this solution here. This is an approximate solution. There is a precise solution to get the M. And this can be made adaptive, so you can have something looking at the output and looking at the distribution and adjusting the M. So it's a very interesting thing. JPL, NASA JPL uses this in a number of source codes, and in fact they have different contacts, for adjusting this M. Because if the M is not well tuned, well adjusted, the performance is not so good. But if it's well adjusted, then it's usually within 1% of the entropy. Okay. All right, now we come to another topic, and that is transmission over unreliable channels. Then the model is a little bit different, and the problem is sort of the dual of the original problem. We were looking at a problem of trying to get rid of the redundancy. We're trying to get anything that was like excess weight or humidity. You want to get that piece of material completely dry. You want to get all the water from the thing. Now we want to put the water back. We want to introduce some redundancy. So the original problem is analogous to sphere covering. We talked about lattice this morning with Professor Suri, and she was talking about covering. You know, you want to have a very effective way to cover the space. The original problem was a sphere covering problem. Now we're doing a sphere packing problem. In the sphere covering, you want to cover the sphere with a minimal number of spheres to reduce the bit rate. You want to have a small bit rate. Over here, I want to have a high bit rate because I want to transmit a lot of information. So this is the sphere packing problem. I want to have many spheres in the space that I'm allotted to have. Okay, so this is very much similar to the model that we have here in the banner. We have a channel encoder, and this is a message. The message can be from an integer set. The content of the message, you know, there's an interesting statement by Shannon in his paper saying that you know, the focus is to transmit information from one point to another, and sometimes, often, this information makes sense. But if it makes sense or not, that's completely irrelevant. You know, it may be some like soap opera, completely irrelevant, but you know, that's the information they're trying to transmit. So here is the information, and we can just label that as integers from 1 to 2 to the nr. And we say that the r is the rate of the message. So that's the thing that we want to be increasing. And n is the number of uses of the channel. Now, we don't do that in a single shot because we'll see that it's very efficient to try to do that. Sometimes the channel is benign and allows you to do just that in a single shot, but usually it's going to require a long string of channel uses. So that is the message set. This message set is going to be mapped through a channel encoder into a code word, which is a series of symbols from a particular alphabet that is placed in the channel. And then there is distribution here of the output given the inputs, a conditional distribution. And we are assuming, even though it's not stated here, that this is a memoryless channel. So it doesn't look, and it doesn't have an effect on the output from previous symbols that were transmitted. So the symbol Y in the present depends exclusively on the symbol in the input at the moment, not on past symbols. So it's a discrete memoryless channel. And then you have a decoder that does the opposite operation, trying to get a decoded message here. And the probability of error happens if they are different. Okay. Now let's look at some examples. This is a noiseless typewriter. So that's the one that we don't need coding. Now we can just put symbols here and they go out to the output with no problem. The question that we ask is, how many noise-free symbols are there? In this case, there are 4. Then the rate, and in this case is capacity, is logged to the base 2 of that number. Same number here, and that means that we can transmit 2 bits per transmission. Great. Well, how about this one here? Well, the 2 and the 4 are not even being used, right? And how many, I ask again the question, how many noise-free symbols are there? In this case, there are 2. Even though you have 4 symbols in the output, there is probability half of a transmission from a 1 being represented as a 1 or a 2 in the output. Similarly here. So this gives you log 2, which is 1 bit per transmission. Okay, let's make it a little bit more involved. Let's include that. Does that help? No, that doesn't help. It's going to still be only 2 noise-free symbols, and still the rate that I can transmit, and that's capacity, is 1 bit per transmission. And also, if I go for an extension of this channel, using many uses of the channel, that's not going to help. This is capacity. Okay. Now let's do this. Okay. Now it's a little bit interesting because, you know, there is nothing really saying that these symbols are separate. You have to do that separation yourself. You know, it's like you have a swimming pool full of chocolate, and you realize that you cannot eat that chocolate, all that chocolate, because you're going to have some indigestion. Okay? So you have to exercise some moderation. This exercise of moderation is coding. You say, okay, let me calm down, you know. I have to, so basically what you do, you can, in this case, use only 1 and 3 as your input. And then you're going to have 2 noise-free symbols, and you're going to be able to transmit 1 bit per transmission by using only x equals 1, x equals 3. Of course, you can also use all of them, but then you're going to use n going to infinity. You cannot do that in a single shot anymore. Okay? But the interesting thing is you can say, okay, I don't care about this input. I'm going to use, Shannon code, random coding, and so forth. That's fine. But then you're going to have to go with n going to infinity, and the capacity is going to be the same, 1 bit per transmission. Well, this one is nice because bits are, from a binary alphabet of size 2, and here we have 4 possibilities. What if I now add another one, a 5th output? Of course, I can still send 2 noise-free symbols by just looking at this 1, 2, 3, 4, and I send only 1 and 3, and I don't care about the 5. But now I'm actually throwing away something, some resource. Before I was not throwing away anything. I was completely efficient. But if I throw away the 5, I'm going to be throwing away some resource. And it's interesting that there is no code that we can use efficiently with n equals 1 for this application. By the way, this codes here, for example, if I use 1 and 3, actually I'm getting the output with probability of error equals to 0. Okay? Which is a strong thing. Usually you're not really looking for probability of error equal to 0. You want to have arbitrarily small probability of error. That is the criteria for reliable communication. You want to have it 10 to the minus 200, 10 to the minus 300, anything. But if you require it to be 0, sometimes the capacity is 0. Sometimes you're stuck. In this case, it happens that the capacity, zero error capacity, is 1 bit per transmission. And here, the 0 error capacity is more than 1 bit per transmission. So in other words, you can have more than 2 noise-free symbols here. And we'll see how we can do that. And this is an interesting example that has a 0 error capacity that is different from the Shannon capacity. The Shannon capacity is the one that is for arbitrarily small probability of error. And we'll see that they are not the same for this example. Okay, so I just mentioned that for n equals 1, there is no efficient way to do a good transmission here. Of course, you can just limit yourself to 2 noise-free symbols, and you can get 2 bits per transmission with 0 error. But now consider that we have the second extension of the channel. In other words, n equals 2. And I want to have here code. In other words, I'm going to populate this chart, which represents the x1, in other words, the first letter of the code word, and the x2. Which code's square should I pick? Okay. Well, let me suggest this code here. Okay. So that is the positions that I'm going to be transmitting. In other words, one code word is the 1 code word. It's represented here in green. Okay. And the 2 3. Notice that these are almost like knights in a checkerboard, in a chessboard. You jump with the knight here, and then you jump here, but then you complement that, like a Taurus, and that would be the position here, and then another knight jump here. So that is an efficient way to populate that. Let's see what happens. Just to remind you of the channel, if I send a 1 1, yes, and 1 1. So what are the possibilities in the output? It's going to be 1 1 or 1 2 or 2 1 or 2 2, right? So now I populate the outputs. And now I'm looking at y1 and y2. And from that 1 1 in the x1, x2, I can have all these guys here coming in the y1, y2, and similarly here and so on. And you notice there are still some that are not used, and that's some inefficiency. If we go for n equals to infinity, they're going to be used, and we're going to be more efficient. That's why Shannon capacity is a little bit higher than the capacity that we can get here. Well, what is the rate that we're getting here? How many noise-free symbols are we getting? 5, right? So I have log of 5 information, but now I have to divide by 2 because I did 2 transmissions. So my rate here is log of 5, which is the number of noise-free symbols, but I have to divide by 2, and that's 1.16, a little bit over 1. The Shannon capacity, you notice that we gained from the original basic code of sending only 2 noise-free symbols. Would have a population of 20 here, and there are 25 positions here, right? And would have actually 16. So we increased to 20, and we still have 5 that are not used here. Well, those 5 that are not used account for another 0.16 in the bits per transmission that we can get with Shannon capacity. Okay, so pretty much this shows us that we want to separate the outputs in bunches so that they can be decoded efficiently. Well, how about this? How many noise-free symbols are in this channel? This is the binary symmetric channel, very famous channel. Okay, well, clearly for n equals 1, we cannot do much, right? How about using n large? And that's the idea. So the idea that Shannon had was to look at n uses of this limited set that's the code book. The code book is not the whole swimming pool of chocolate. It's just have some chocolate, but exercise some moderation. And then what is the moderation here? Well, I want to have a situation that at the output, they would not be overlapping. Okay, they would be separate shadows of each code word here. And then I can tell, oh, this one is from here, and that's okay. How many I can do? Well, that is the second theorem of Shannon. The first one was related to coding a source. The second one is this one. He defined this information channel capacity as this number, which is the maximum mutual information for maximization here over P of X. Notice that the mutual information is a function of the joint distribution P of xy, which can be written in this form. But P of y given x, that is fixed by the channel. So you really can only vary the P of x. And you notice also, remember, that we said that this is a concave function of P of x and a convex function of P of y given x. So in this process, we are trying to maximize the concave function. And there is a solution for that. And the theorem that Shannon had was, for a discrete memoryless channel, all rates R below the information channel capacity C, which was defined just now, are achievable with maximum probability of error, arbitrarily small. Maximum probability of error, not even average probability of error. And conversely, and that's usually we refer to that the converse part of the theorem, if the rate is above C, the probability of error is bounded away from 0. You cannot get to 0. In fact, there is a form called the strong converse that says that if you are in this region above C, the probability of error is going to go to 1. So it's very drastic. So the proof of that, I'm going to mention something about achievability. This is just an outline. Using random coding, we generate codes with a particular distribution P of X in the code words. Then we can show that the average probability of error tends to 0 with n going to infinity if R is smaller than C. So there are 2 exponents there, and the exponents, if you have R smaller than C, the exponent is going to be negative, and then as n increases, you're going to have a decreasing average probability of error. The advantage of doing the random coding is that you don't have to worry about particular codes. You just do any code, do the average of all possible codes. And then, okay, the average is good, then there must be at least one code that's good. You take a code that's good with the average, and then you expurgate half of the code words that have more than that probability of error. If the average is P of E, then there's going to be at least half of that number that's going to have probability of error 2PE. So you double the limit and you can restrict the number. That expurgation is going to cause a very minute decrease in the rate that is going to go down to 0 with n. And then you can have a code that has maximum probability of error limited to what you want. It's not going to be epsilon, but 2 epsilon, but essentially they are the same, small. So you can start with epsilon over 2 to get that. Now let me try to prove a converse in a sketchy way. The formal proof for the converse usually is the funnel inequality. I mentioned that funnel was there with Shannon, and he contributed with this very fundamental inequality called funnel inequality for the converse. But there is an interesting geometric proof that is really a sketch that we can use using the asymptotic equipartition property. Well, we know that, you know, after n implementations of this, the size of this set here of all the y's is going to be approximately 2 to the n entropy of y. And the size of the typical balls, you know, coming from each code word, each shadow here, is going to be also 2 to the n, but now it's the conditional entropy of y given x. Well, if I want to have these balls not overlapping, even if I consider that they are very efficiently packed in the overall space, how many balls can I have? It's just the ratio, right? So I can have 2 to the nh y divided by this number. That's the whole space divided by the size of each one of them. And that's 2 to the I, and that has to be smaller than c, because c is defined as the maximum I. Okay? So that means that this is the number of R of code words that I'm picking, right? Number of balls that I'm placing in that volume. So that has to be smaller than 2 to the c, or R has to be smaller than c. But the formal proof uses funnel inequality. This is just a sketch. Okay, now let's then look at the binary symmetric channel. It turns out that the maximum mutual information can be represented here is the entropy of y minus entropy of y given x. The entropy of y given x is going to be essentially independent of x. It's going to be the binary entropy function evaluated at epsilon. And the maximum entropy of the output is going to be 1, which can be obtained when you have uniform distribution here on zeros and ones. So this is 1 minus h of e, which is this plot here, not so neatly drawn, but that is the idea. You have a capacity that goes down like this and then goes up again. Of course, you can invert the outputs if you have more epsilon greater than 1/2. And you notice that if epsilon is 1/2, then the capacity is 0. There's no way you can transmit information. And just to have an idea of how much it is for something smaller here, the entropy, the binary entropy function for 0.1 or 0.9 is about 1/2, very close to 1/2. So just a ballpark number here. If you have a 10% value on the epsilon, you're going to be transmitting 1 bit per transmission, reliably, with n going to infinity. Okay, there's no way you can have finite n or small n to get arbitrary small probability of error. Okay, this is another example, the binary erasure channel, where we introduce an erasure here, and you notice there is no crossover probability. So we have this distribution here in the channel. And again, if we maximize the mutual information, you can write it like that. Not difficult to see that this is going to be 1 minus alpha. So it's going to be like this. It's just a linear decrease with alpha. Of course, if alpha is 1, there is no way you can transmit information. But the capacity is achieved here with uniform distribution on zeros and ones. Okay, so it's very used channel, very much used channel. The Z channel. This is a particular Z channel because, you know, I put half and half here just to simplify the calculation. But I suggest that you use this as an exercise. Try to get this maximization here. It turns out to be log 5 minus 2, which is 0.3 bits per transmission. And the maximizing distribution is no longer half and half. It's kind of intuitive here. Probability of 1 should be 2/5, and probability of 0 should be 3/5. Why is 0 more likely in the optimal distribution? Because 0 is more reliable. There is no noise associated with 0, but there is noise associated with this guy. This represents, in a way, the photon channel. You know, like if you put no photons in a fiber, there will be no photons on the other side. But if you put a photon here, maybe it will be absorbed or something. If you put very few, you know, photons, you may still get a 0 at the output, because the this is Poisson distributed, so you can have something that was transmitted but was not appearing the other side. Okay. A noisy typewriter, that's an example of a symmetric channel, and this is a sort of an expansion of the one we saw before. By the way, for this to be like what I'm representing here, I need to have this half and half. If it's not half and half, then you can use that to increase the capacity. Okay? But so the entropy of y is going to be log of 26 because that's going to be uniform with uniform distributions here. Minus log of 2, which is the entropy of y given x, which is essentially this output here for each one. And that's going to be log of 13. This is an interesting example also because the solution can use uniform distribution on the inputs for using a random code, Shannon style and going to infinity. But in this particular case, you can use just n equals 1 and limit yourself just to alternating symbols here. So for this example, you can just have the same rates by alternating, using the alphabet A, C, E, and so forth, like we did in that earlier example. Okay. Okay. Now we go to another chapter, differential entropy. I like to call this relative entropy, but relative entropy is the name that's very much associated with the Kubek-Leibler divergence. So, but you'll see why it really should be more of a relative entropy. It's not an entropy in the sense that this can go negative, as we'll see. But it's almost like a direct extension of the earlier definition. We just substitute the sum by an integral. And the support S is the domain of this integration. We have minus integral of f log f. And f is the density. F is not a probability. It's a probability density. So there is a big difference there. The probability density can be greater than 1. They are all positive, but they can be greater than 1. They integrate to 1, right? The integral is 1. But in a particular point, they can be more than 1. Probabilities, no. Probability masses, they are always between 0 and 1. Because they are positive numbers that sum to 1, so they cannot be more than 1. But here, since it's an integral, you can have instances where they are more than 1. And that, creates some problems here. For example, if we have the uniform distribution, in the interval from 0 to a, the density is just 1 over a. If we integrate that, then the entropy is going to be, the differential entropy is going to be log a. And for a less than 1, this is going to be a negative number. So one interesting aspect is that 2 to the h, just like the AEP, by the way, the AEP also applies here. It's going to be 2 to the log a, which is a, and that is the size of the support set, which is a non-negative number. Okay? So I can still have something that's non-negative by looking at the 2 to the h. But the h itself can be negative. Here's an example for the Gaussian distribution. It's just a simple integration here. Good to do as an exercise. Then I'll suggest that you also do the exercise for the multivariate Gaussian. It's a little bit more involved, but we'll have the answer. This is a very nice answer. 1/2 log of 2 pi e sigma square nets. But then I can move this to log base 2, and then I have it in bits. Just that usual change of base. Okay, what is the difference? What is the relationship between differential and discrete entropies? Let's suppose that we have a quantization of x, and we denote it by x delta. And delta is the level of that quantization, it's the spacing here. So, and we consider xi as being, say, the middle of the interval here, of the ith interval. Now, the entropy of x delta, that's a discrete random variable that has a bona fide entropy, and we present that with a capital H here. And that is minus summation on I of pi log pi. So that's a discrete random variable. Now I approximate the pi by the f of xi times delta, okay? And I put that approximation everywhere. Now I can break the product here inside the log and putting a delta outside, and you'll see that it's going to be isolated because the integral of delta f is just 1. Or the sum of delta fi is going to be 1. So you're going to isolate that term. And this term here is going to be like, this delta is going to be like the dx of the integral. And we're going to have the entropy of, the differential entropy of F here minus log that. In other words, they are related by this level of quantization. And the reason why this can be negative is that this makes up for it. Now, this is going to be a positive number that makes sure that this part here is positive. So this is, in a way, a relative entropy. Is relative is entropy that is relative to the level of the quantization, and that relates to the true entropy of the discrete distribution by this expression. So the two entropies differ by the log of the quantization level. And we can define also a joint differential entropy, conditional differential entropy, Kubiak-Leibler divergence, mutual information, with some care for avoiding the infinite differential distributions. Sometimes different differential entropy. Sometimes if we do the calculation, you have all the distribution condensing in a particular subspace, and then you get this infinity bothering sometimes. So to avoid that, my suggestion is, well, there's no problem here with the divergence. And to use the mutual information, instead of having the expression that says x minus entropy of x given y, use always this one here, the one that comes out from this. So you have the entropy of the joint entropy with negative sign, and then the two marginal entropies, h of x and h of y. And then you're not going to have problems with this infinity. I mentioned the multivariate Gaussian. Okay, so here's the result. If we have a multivariate Gaussian with mean mu and covariance matrix K, this is the result for the entropy. And here we have the determinant of the covariant matrix. Notice that mu doesn't come in here. And that's very intuitive because it doesn't affect the entropy. You can just shift the distribution by having any type of mean, and that's not going to affect the entropy. Just algebraic manipulation, interesting as a nice homework. Okay, now we come to the Gaussian channel. The Gaussian channel is very important because it models very well, for example, the channel that you have from transmitter in Mars to Earth. Okay, why is that? Because the noise that you get is coming out from many independent contributions, small contributions. And when you have a large number of independent contributions, no matter how distributed they are, the sum is going to converge to something, right? It's the central limit theorem. It's going to be converging to a Gaussian. So the noise tends to be Gaussian, and this, again, we have here a set of messages that we would like to transmit. These are the code words. And now we have to put some limits here on the x, because otherwise I can use infinite power and transmit at infinite rate. Okay, so that's not fair. You know, I don't have the whole line to transmit. I have to restrict myself, again, using moderation, to make sure that I satisfy the power constraint. And then there is noise that's added here. I'm representing this in vectors, so the noise here is essentially noise n times the identity matrix to characterize the covariance matrix here, the noise. But it's independent noise, independent from use to use. Okay, and so everything else is the same. Now what would be the capacity? Turns out that the capacity is the same expression, but now the maximization is over the f of x. That satisfies the power constraint. And it's a simple exercise. We can divide again the I into h of y and h of y given x. This one here, we can notice that y is just x plus z given x. Well, if it's given x and they are independent, I can just remove, this is going to be h of z. But h of z, I know what it is. It's 1/2 of log 2 pi e times n. And this one is going to be maximized if I make it Gaussian. So the best distribution for the source, for the input, is going to be Gaussian, because that's the only distribution that will imply that y is also Gaussian, and therefore of maximum entropy. So if we put y Gaussian, we're going to have here p plus n, that is the variance of y, because it's the sum of x plus y, and they each have variances p and n, and they are independent. And here is the entropy of the z, minus 1/2 log 2 pi z. Notice that the 2 pi e will cancel, and we have just p plus n over n, and that can be represented in this format. Okay, so that's the famous Shannon expression for the capacity of a Gaussian channel Notice that this is the time discrete channel. So I'm using the channel in some predefined times. Okay, I put a signal, and it's red on the other side. Then I put another signal, and then you coalesce all the signals from the other side, and you have a code word, and then you decode. So the amount of information I can send per transmission is this in bits. Some people say, well, but how about using the time continuously, you know? Well, for that I can do, but then I have to also associate a bandwidth constraint, okay? How fast can I move this signal, right? So let's look at that. So just finalizing what we said before, the capacity of a discrete time additive Gaussian channel is this one here, and it's achieved with Gaussian inputs with probability P. That's how we generate the random codes, with a Gaussian input with probability variance P. Okay, now the bandwidth Gaussian channel, consider a continuous waveform input. In other words, now we have the power constraint being represented in this format. X squared integrated from 0 to t divided by t has to be smaller than p. Okay, so that's the power constraint. And there is also a bandwidth limitation to w. Okay, there is some confusion here. I didn't want to use more notation. The w is also the massive set. But please, you know, take note that this is a different w. From the context, we'll see which one is which. The channel then has white Gaussian noise with a power spectral density n0/2 watts per hertz. Now, what is this dimension here? Watts per hertz. Watts is joule or joule per hertz, right? Energy per time. And hertz is cycle per second or cycle per time. It's 1/second. So this is essentially joule. This is an energy measure here, n0/2. And in the interval from 0 to t, we can specify the code word by the Nyquist sampling, you know, by having 2 WT samples. That's the number of dimensions that we have on a bandwidth limited signal in a time t. We can think of that as the number of degrees of freedom. Okay, so I can represent that signal that is associated with a continuous waveform essentially as 2 WT samples, and those samples I can send on a discrete time channel like this one, you know, and I know the capacity for this one, so I can use the answer for this problem to get an answer for this other problem. And looking at that, you know, realizing that the noise associated with each of the sub-channels is going to have a variance of n0/2. This is not difficult to get. You just get the power in the whole bandwidth and divide by 2 WT, and you get this. Then we're going to have this capacity. Notice that the 2 that we had here went away. And that's because we have usually the W representing just the positive part of the spectrum, that there's another W in the negative part. So that's why that 1/2 disappeared here. And here I have again the power, and here I have the total noise power, which is N0 times W. Notice that it's N0/2 times 2W, and then the 2's cancel here. And now it's bit per second. Okay, so that is a very appealing number. This is the capacity of a channel. If you have a bandwidth limitation and a power limitation, this is the capacity. That's how much information you can have on that channel. You cannot send more information than this. Now, suppose you're considering sending information from Brazil to Africa by shaking the ocean, you know, and of course your power is not too big, and you know, it's not clear what is your W, but you can shake it pretty fast, right? So there's going to be some number, and you're going to be able to transmit. I mean, it may take ages for the other guy to get the message, but there is some capacity there. And we're, you know, it's apparently funny, but, you know, how about sending from Jupiter to Earth, or from Pluto to Earth? That's pretty much the same thing. You know, it's a very minute thing. You don't have a lot of power over there. You usually have to have a plutonium-based generator because there's no sun, also no solar panels to generate electricity. And if you have a plutonium, then when you shoot this up, you're going to have all sorts of requirements not to have that coming back to Earth and contaminating the whole thing. So it's extremely complicated to put a spacecraft on Pluto or Jupiter and have that transmit information to Earth. And then, of course, they have to rely on very good codes. Okay. Now, one thing that's interesting that I like to highlight is the so-called Shannon limits. We haven't seen really the Shannon limit yet, but look at this expression. C equals W log pa 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 pa. Now, what is power? I can represent the power as the energy per bit times the rate, right? The rate is bits per second, and the energy per bit is in joule per bit. So the bits cancel, and I have joule per second, which is power. And so I can represent that. And if W goes to infinity, this here, it's gets to a limit that is P over N naught log e to the base 2. So even if the W goes to infinity, your capacity is not going to infinity. You have a limited capacity, which is this. Okay? Now, if the power goes to infinity, then the capacity goes to infinity. But the bandwidth, having more dimensions to explore doesn't buy you anything. It's almost like you have thousands of tickets that you can buy to go on a particular trip and put your friends on this trip, but there is only you don't have sufficient money, right? Money is the power here. The seats in the airplane are the dimensions, are the W. So you can have a lot of W, but if you don't have the money, you're not going to take your friends in the trip, right? There are situations when you have a lot of money, but there are no seats. The W is limited, and then you have to come to these numbers here. Well, let's see how much you do the composition of the two. Well, let's now have this number here, R over W, which is the rate that you're transmitting, divided by the bandwidth, okay? So this is something that's measured in bits per second per hertz. Okay, that's the bits per second per hertz. And the power, I'm going to write it as the energy per bit times the rate, where EB is the available energy per bit. Okay, notice that EB over N naught, the two are measured in joule, so this is going to be a-dimensional. Also, we can think of R over W as being somewhat a-dimensional because it's bits per second per hertz, bits per second per cycles per second, so the seconds cancel out, and it's a number that it's a little bit very close to being a-dimensional, if you look at it in this perspective. Now, doing this substitution here of Ni per R over W, I can write R over W has to be smaller than the capacity over W. Okay, now I write the capacity as the expression before. The W's cancel here, and then I have log of 1 plus EBR over N naught W. Okay, now I basically separate this. EB over N naught is going to be here, and R over W I'm going to be writing it as Ni again, and here is Ni again. So I can invert this expression, and I get this one here. EB over N naught has to be greater than 2 Ni minus 1 over Ni. This relation defines the so-called Shannon bound, and it's represented here. It's this bound. In other words, no communication can exist above this line. Nothing can exist above this line. Everything has to be restricted to this, because you want to have larger energy. It's easier to have something with larger energy. And if you say, okay, I have infinite bandwidth, so I can restrict my energy to the minimum, well, it's going to come to a point where, minus 1.59 dB, that is the minimum EB over naught that you can have, regardless of W, okay? Now, if you want to have your W a little bit smaller, in other words, use Ni that's with a higher, with a different spectral efficiency, okay, by having higher rates per band, then this is what you get when you have higher constellations and so forth. It's very difficult to get very, very high Ni because, you now having 64 QAM or, very, very large constellations, the probability of error starts to come in. That's what you do when you have a limited bandwidth. You try to explore the power that you have. So you put people one top of the other. You know, I have the money, so I can put it. I don't care if there are only so many seats. I can have the money, so I put more people in, you know. And then you have to pay, of course, accordingly. Okay, so this is the limit that you get, and this would be the ultimate Shannon bound for irrespective of the bandwidth. All right. Now, Shannon's water filling solution. Question?
What Shannon capacity that we investigated for regard W goes to infinity?
Yeah.
Are we assuming that noise power is infinity at that point?
The what power?
Noise power.
No, the noise power, it has a finite power spectral density. Okay? So the spectral density is finite. If you're going to be using it infinitely, of course, it's going to be adding up. But you're going to have to cut at some point. You know, when you have a sufficiently small probability of error, then you say, okay, so much. Otherwise, also the delay is going to infinity. So you're not going to have time to decode because you're not going to finish this transmission. So there is also the delay problem. You know, there was a presentation I noticed that is going to be talking about finite delay, which is very interesting. It's a big problem. You know, the delay. Two things that Shannon didn't consider: the complexity. And he said, okay, there is some code, but I don't care what's the complexity, and the delay also. You know, and delay is important. You know, if you switch your channel on a digital TV, you see how long it takes to resync. That's all processing delay. It's not the transmission delay. Used to be there was transmission delay because it would go to the satellite and come back. You know, each hop is like quarter of a second. So you know you'd have multiple hops and you had problems. I took this picture recently in a place in Marin County, just north of San Francisco, and I said, "Oh, this is water filling." You know, that is the solution. And suppose we have a parallel Gaussian channels, and here the channels are like the earth, right? They form the base, the noise. If we could put the signal over here, then we'd have infinite capacity because there will be no noise. But the well is restricted to be, you know, some level above the zero level. So that's how we put the power. And I thought I didn't want to put numbers here because that would contaminate the picture. I think this is nicer as it is. And for looking at the numbers, suppose we have 3 parallel channels with noises 2, 1, and 3, which are essentially this one here. Okay, so this is a 2, a 1, and a 3. These are the noise levels. And I have available power of 2. How should I allocate the power? Well, the capacity is going to be, again, for each subchannel, I use the expression of the power that I allocate divided by the noise level. So it's going to be 1/2 log of 1 plus half over 2. And that means that I should put here half over 2, okay? And here I put 1.5 over 1. So that's, oops, that's this here, 1.5 over 1. It's approximately these numbers. And over here I put 0 over 3. In other words, I don't put any power on the 3rd channel because it's too noisy, okay? So the water filling solution is essentially that. You know, this is a very simple result from a maximization with a constraint on the allotted power, and you do that using a Lagrangian. It's very simple, but sometimes, you know, the answer is more appealing than the whole process. So no power is allocated to the 3rd channel. It's not a very democratic thing. You know, say, oh no, let's have power for everybody. No, you're really gonna get power for those that deserve it. Okay. All right, now we come to rate distortion theory, and we still have some ground to cover. As I mentioned, this is the dual of the problem. Now, I want to have a cover, right? I want to have this source well represented by a finite number of points here, because then I can represent them with an index that's small in terms of bit length. So essentially, I want to have this covering here of the space. You know? And for each of the spheres, I have associated one particular reproduction space. Okay, so turns out that we should also define a distortion between the actual source output and the representation. And that can be, it's part of the problem. You need to define that. It's essentially a function that goes from the Cartesian product of the source alphabet and the reproduction alphabet mapped into R+, into non-negative reals. Okay, and we want to find 2 to the n r x's representing representations. These are like the deputies that represent the community, or the sandwiches in that menu of sandwiches that I mentioned to you yesterday. And a mapping, associated mapping, to get the representatives associated with each of these source outputs, such that the expected distortion is smaller than a certain number d. Okay, let's call this equation clubs. Okay. Now the theorem, this was not from that original paper by Shannon. This was again by Shannon. Shannon strikes again in 1959, and he showed that this is possible if and only if. So there's a converse as well. If r is smaller than this function r of d, that is calculated as the minimum over all possible conditional distributions of x hat given x, satisfying the distortion requirement of the mutual information of x and x hat. Again, the mutual information coming up as a key element in the representation. So notice, before we want to maximize the mutual information, but we were doing it as a maximization over p of x. Now I'm doing the maximization over this. This mutual information is always a function of the joint distribution. And now I can write the joint distribution as p of x times p of x hat given x. And this is the part that I can have some flexibility over, because p of x is fixed by the source. Now it's the other part that's fixed. And now this is a convex function of p of x hat given x, and it has a minimum. So we can work that. Now let's look at this. Let's calculate this r of d for a binary source. Then for a binary source, we can write the mutual information of x and x hat, and we can, it's not difficult to get it simplified to this. Here it is. We have the mutual information, h of x minus h of x given x hat. Now x is just x plus x hat. I mean, I can generate that because I have x hat, right? So there is no extra uncertainty about this thing. Now, if I drop this conditioning, what happens to the entropy? It increases, but there's a minus sign. So it's going to be, this is going to be smaller. And this is essentially the distortion. So this is h of d. So here I have the binary entropy functions evaluated in p and d. And if I look at this function, another thing is that this is a bound, right? So far is a bound. I have to show that I can achieve this bound. To achieve this bound, I look at this test channel. Sometimes there is some trial and error. And this test channel is a test channel that generates x hat and x with the appropriate distribution to get that mutual information. And it is going to have a probability of 0 being this number, probability of 1 being this other number. And of course, x has to be probability of p for being 1. And this is the distortion d. So this can be achieved. And that means that the rate distortion function for this source and distortion is this. It's just essentially the entropy of p minus the entropy of d. Notice that this is a part of that binary function, binary entropy function. If we plot it like here, suppose we're plotting like this, okay? And when it gets to this point, because p is smaller than 1/2, then we can just take it as 0. In other words, if the allotted distortion is so large that is below the R&D, then you just represent it with rate 0. You don't represent it. In other words, you represent the source by the mean. And for that, you don't need any rate. Okay? So that would be, no, so far we were doing the compression, data compression, or the source coding problem, looking at 0 distortion. Okay, 0 distortion is lying here. You need to have a rate that's above the entropy, okay, which is in this case a binary of h of p, because the source has probability p. If probability of p is 1/2, then it's going to start, no, it's going to touch here just at the minimum point. Okay. All right, let's have one that's a little bit more perhaps usual to see. It's the Gaussian source with an MSE distortion. And then, again, we can do the minimization of the mutual information. We get this number. Here it is. We can write the mutual information between x and x hat as h of x minus h of x given x hat. And then we do the same type of bound, and we get it in this form. And this is the answer for the rate distortion function. Okay. Again, if d is above sigma square, we just represent it by 0. Because if d is above sigma square, that's saying that I'm trying to represent a source that has, say, variance 1. But I accept distortion 2. So, okay, then I just give you the mean. The mean is 0. I don't give you anything. You already know that the mean is 0. So the rate is going to be 0. And again, here's the shape. In this case, it's not coming out of a finite position anymore. It's coming out of infinite, right, all the way there, because it's a continuous random variable. If you want to have 0 distortion, then you're going to have infinite rate. Okay? So it comes all the way from infinite like that, and then at this point, sigma square, it's just flat and 0. Okay? So there is a nice rule of thumb that we can get from this expression that I would like to pass to you, and that is inverting this expression here for the distortion. Now we can invert the r and d to get the d over r, the distortion rate function, and that is due to the minus 2r times sigma square. Okay? Now, what would be then the maximum signal-to-noise ratio that you can have with this system? Of course, this is for Gaussian, and it's IID Gaussian. Turns out that this works extremely well for just about any type of source. And for example, audio. If you have an audio system, you can look at these numbers. Because then, if you look at the signal-to-noise ratio in dB, it's going to be 10 log base 10 of the signal power, which is sigma square, as we saw, divided by the distortion that you're getting here. So if we plug this expression over here, we're going to have 20R times log on the base 10 of 2, which is 0.3, and so then you get approximately 6R. And that is the rate that you have. R is the rate in bits per source sample, and so this expression here is just the dB signal-to-noise ratio, so it's adimensional. The bits per source sample refers to the R here. Okay, so 6R is what you get for the signal-to-noise ratio. That means that if you have a 16-bit per sample audio system, you're really getting something like 96 dB of signal-to-noise ratio, which is a very decent signal-to-noise ratio. Usually for images, we want to have something 50 dB for images, but the ear is more demanding. Usually you want to have something like 70 or more dB for signal-to-noise ratio. Okay, we come to Kolmogorov complexity. This is a very completely different way to represent uncertainty and the intrinsic complexity of an object. So Kolmogorov was looking at a way to represent an object, and he was wondering how complex is this object? How can I associate a number to represent this complexity? And he noticed that this has to be associated with the difficulty that we have to represent it, to describe it. So this description, this descriptive complexity, can be now quantified by the minimum length of a computer P, a computer program P, that when fed to a universal computer will output X. So that would be the complexity associated with an object X or a string X with respect to a universal computer U. Okay, so it's the minimum length of the program that prints X. Okay, and stops. Okay, of all programs that print X and stop. Okay. Now, suppose now I have a different computer. So this shows that there is some criteria for the universality of the computer. Well, if I have a computer A, then I can always associate the complexity with respect to the universal computer and the complexity with the rest of the A computer by having a description of the A computer. That's going to be a constant. It's going to be a large constant, but I don't care, it's a constant. And doesn't depend on X. Okay, so there is universality in this respect. By the way, Commodore complexity doesn't worry about constants. If it's something is constant, for him, it's just like nothing. You know, he wants to see how things depend on the n, on the parameters that are associated with the object. Okay. And another thing is that Commodore complexity is not computable. You can have only bounds. Because if you show a program that works for printing X, that means that it's an upper bound. Who says it's the minimum computer length? You know, you don't know. So there is this tricks. Now let's look at some examples here. Suppose you have a repeating sequence, 0, 1, 0, 1.
Undecidable.
It's non-computable. I don't know if it's if you have a bound, then you can at least start to diminish the domain. Okay, so if you have a sequence that's just 0, 1, 0, 1, 0, 1, the complexity given the length of the computer, sometimes we put a conditional here on the length of the X, it's going to be sub C, right? So it's just a print alternating binary digits of length C. That's the program, and that's some constant. Okay. Here, the L didn't have to be part of the description because it's already given here. Now, suppose now we have some arbitrary sequence X. Again, this is a bound, right? I can always say a program prints this sequence and then X. I will put the sequence. So the length of the sequence itself is plus a constant, is a bound for the Commodore complexity of the sequence. Now, here's another upper bound. Suppose that I have the unconditional Commodore complexity of X. It's going to be smaller than the complexity when I condition that on the L, when I know the length of the sequence, plus this is a bound. So I have 2 log of L, because I don't know what is L, right? I mean, from this perspective here, I don't know what's L. From here I know, because it's given here, but from here I don't know. So I have to represent what is L. What is the length of the X? So you tell me, I have an integer for you. I say, okay, I need to have some bits to represent it, you know. I mean, maybe I'll just take my chance and say, I'll give you 100 bits. Is that enough? And said, no, I need more. So how many bits do you need? It's not written anywhere, right? So this has to be conveyed. So one way to do this, it's a very interesting way. It doesn't look like it's very efficient, but it's very simple. It's like Golomb code. Maybe not the most efficient, but it's very simple and does the job. You just take a representation of L by repeating every bit in the binary representation. Like, suppose it's 5, so you go 1, 1, 0, 0, 1, 1, and then you use 0, 1 to terminate. Okay? So that's going to be log of L times 2, because you're essentially doubling the whole thing, plus a constant to tell the computer what to do. Okay? So this is a bound. Now, suppose you say, okay, I'm not liking this inefficiency here. Once I have log of L, I can represent the number of bits that I need to represent log of X. Log of L, right? So I need log of L. So I can need log of N. And then what about this? You also need to represent that. So you go log of N, and so on. And then this has this notation here, log star of N. There's a lot of work being done in this. This is actually an active area of research, you know, how to come up with some efficient ways. Okay, I'm gonna have to skip some stuff. There are some examples here and there. Sometimes, I mean, it's like, of course, the complexity of the sum. You can describe one and describe the other and then just tell the computer what to do. And so you have these bounds. Pi is a nice number. What is the complexity of pi? It's, you know, you just tell the computer, divide by, you know, the diameter by the circumference by the diameter, and with the precision that you want, you know, and that's a constant, okay? So no need for... Now, if you want to have the n-digit representation of pi, then you need to have a complexity of n, and that could be log star of n, and so on. Okay, now monkeys in a computer. Perhaps we can go this very quick. Monkeys in a computer is nice. Suppose, what is the probability that a monkey typing on a computer will produce a sequence of n zeros followed by anything, a sequence of n zeros followed by 1 and then followed by anything, and then the works of Shakespeare followed by anything? Okay. Well, it turns out that the probability of a computer, with a random input, as the monkey would certainly produce, unless it's a very educated monkey, will type X followed by anything, is the sum of the probabilities of all the programs that print X, Y, summed over all the Y's, over all the possibilities here. And this sum is going to be approximated by the largest term. And the largest term is the one that is associated with the smallest description. And it's pretty much going to be this particular term. So suppose, for example, in the case of the first situation there, you only have the n zeros and anything else. You just tell the program, the computer, print zeros forever. In other words, you use the y as being part of that continuation. You don't have to specify the n, because it can be anything. So that program has just a constant length, and then for the monkey to output this in the computer is just to the minus c. Now the other one, because the 1 is breaking here, you're going to have to represent the 1, and that's going to be log star of n minus c in the exponent. And for Shakespeare, you have 2 to the minus n being the number of letters times the entropy of English. And then we can define a universal probability. That's the probability associated with this input being generated by the monkey and the computer, and that's 2 to the minus Kolmogorov complexity of x. In other words, it's very different than typing on a typewriter, because there will be no computation available then. Okay, I'm going to have to skip this. This it's just saying that the programs that halts, their length has to satisfy Kraft's inequality, because no program can be a prefix of another program. And just like the instantaneous codes. Yes? Yeah. This one? This one?
Sorry, I've lost it.
What is the question?
About comparing instantaneous codes.
Excuse me?
About comparing instantaneous.
Oh, instantaneous codes. Okay, that is this one here. For any computer, the sum of the 2 to the minus length of p for the programs that cause the computer to halt, print something or do something and halt, that has to satisfy Kraft's inequality, because no program can be a prefix of another program. If the program halts, it doesn't look ahead. So it has to satisfy the prefix-free condition. It has to look like an instantaneous code. Okay? Then there is this way to associate entropy and Kolmogorov complexity, but I think in the benefit of time I'm going to skip that. Applications to biology. I think I'm going to report basically on something that is really an amazing result that was obtained here at Unicamp by one of our colleagues, Professor Palazzo, and Clarice was his student that was working on her PhD, and there is some other people associated, and they have this nice paper. And what I want to tell you about it, it's essentially the title here. BCH error correcting codes have been found in DNA sequences generated by BCH codes over GF4. So that's the first time. This question has been raised for a number of times. This is the first time that we see BCH codes, error correcting codes, in DNA, in biology. And I asked, and this came out in Electronics Letters 2010. I asked Palazzo, he gave a talk here recently about this, and I asked him, when you present this in biology and other scenarios, are the people very thankful that engineers are coming to the rescue? And he said, no, they think we are invaders. We are invading their turf, they don't like that so much. And in fact, there was a guy who asked me, are you saying that God was a mathematician? I suggested to Palazzo, no, you should say, no, he was an engineer. And somebody else told me, no, he was an architect. And then, it's, okay, applications to economics. I'm just going to give one. Suppose you have a stock market, and there's a portfolio B on the stocks, So B of I is essentially a positive number and they sum to 1. That's how you distribute your money on the stocks. And the stocks is a vector of m possible stocks, but now we can associate also the vector with the time I, that's the day, okay? So I going from 1 through n are the n days of the market. So xi for each particular stock would be represented by the relative price of the final price with respect to the initial price in the beginning of the market. So like 1.03 would represent a 3% variation on that particular day. So the wealth over n days using a certain portfolio B is essentially going to be the sum of B transpose X over and over again, because you're taking all the money that you have, just readjusting it to make sure that you're in the same B, because the variations will change your position. And we are also assuming that there is no commission. You don't have to pay commission to do this. So it's a frictionless world, which is very benign. Usually you don't have that. Then you just invest everything that you had as a return from the previous day. So that's the wealth you're going to have after n days. Okay, the growth rate of the stock market with respect to the distribution F, we associate a distribution F, is going to be the expected log of, this is a definition, log of BTX, B transpose X. And the optimal growth rate, of course, is the maximum of this growth rate over all possible Bs, all possible portfolios. And F is, of course, the market distribution. Now, here's a nice theorem. The optimal wealth after n days behaves like an exponential on n W hat, W star, with probability 1, because that's coming out of the law of large numbers, the strong law of large numbers. And so the proof of that, by the strong law of large numbers, we have the, if we write log of S like that, notice that S is a product, right? S is a product of BT. If I write as 2 to the log of this, I can pass the sum of the log as the product of the log as a sum, and then I have this expression here, okay? And this thing here will converge by the law of large numbers to the average of this. But what is the average of this? That is just the expected log of BTX optimized over B. Okay, so with probability 1, that's going to converge to W star, and then we have essentially the S evolving exponentially to this number. Of course, if W star is a negative number, this is going to decrease. So you have to watch out a little bit. Okay, I still have like 2 minutes. So let's look at multiple user information theory. We can discuss, there's going to be a lot of discussion about this subject in the rest of the school. Professor Chandra Nair just arrived from Berkeley. He's sitting there in the back. And he is going to be talking about broadcast channels. I'm going to be minimizing here a presentation, since this is a nutshell, for multiple access channels, broadcast channels, interference channels, and relay channels. So these channels have their discrete memoryless versions and also their Gaussian versions. And for simplicity, we'll look at the Gaussian models. Okay, so here's a Gaussian multiple access channel. You have 2 inputs with different power constraints, and they sum, there's some additional noise, and here you have the output. So we can think this is the capacity region. It's going to be this pentagon of regions. And you recognize some of these expressions from what we saw in the Gaussian channel. And of course, if you don't care about R2, you can go at 1/2 log of 1 plus P1. Now considering here that we're normalizing the noise to be 1 here. So that's P1 over 1. Similarly here, you have this other one. But when you have the 2 of them transmitting, we can do, this is superposition coding. We can put them in layers. Like that water filling thing, we can put that in layers and achieve any point in this line connecting these 2 extremes. Okay, for the broadcast, we don't get a pentagon, we get a rounded thing, and the broadcast is the dual. Notice that this one has 2 inputs, this is the multiple access channel, 2 inputs and 1 output. Now we have 1 input and 2 outputs, and each one have different noise. This one has noise 1 normalized, and the other one has some additional noise and 2. And these are the expressions that we can get. One way to do that is by superposition coding again. We just put this in layers, and we can get any point here in this curved region. Now, another possibility is the standard interference channel, and this is a channel that has 4 parameters. We can normalize it in such a way that these 2 gains here are 1, but then we have a gain A and a B, and powers P1 and P2, okay? So this can be simplified to the symmetric channel where you have the same powers on both sides, and the same interference gain A here. Now we have only 2 parameters. That simplifies the problem a little bit, but it's still an open problem. This is an open problem. The Gaussian is not an open problem for the, the broadcast channel that we saw here is not an open problem for the Gaussian. This is solved. But for the discrete memberless, it is open. It's still open. You know, even though people are coming, you know, progressing in this, getting closer to a final solution, you know, with better bounds and so forth. So another possibility to simplify it is to look at the Z channel, which is now actually it's a inverted Z, because that's the Z that the Zorro does with the sword. So I prefer that. Okay, so what the things that we can do with interference? No, you can ignore it, just take it as noise. You can avoid it by dividing the space. You know, it's like, so oh, too much noise in this room, I'm going to go to another room. But that's fine, there'll be no noise there, but I'll be in a smaller room. You know, I'm dividing the space. So you can do that too. Or you can partially decode both interference signals, or partially decode one of them and fully decode the other, or fully decode both of them. So these are the strategies that we can get. Some of the history, I'm already a little bit over my time here, so let me just, this is in the notes, so I prefer that you look at this history from the notes. Essentially, the original paper was from Carlyle, and he showed that very strong interference does not reduce capacity at all. You know, if A squared, you know, the gain of the interferences is very large, larger than this number, then you can completely decode the interference, and then you remove it. So interference is somewhat like noise, but not really, because it has intelligence. You know, somebody was conveying information with that, so we can take advantage of that. Okay, and then there were a number of results. This is an important result. Han and Kobayashi put forth the best known achievable region for the Gaussian channel. Okay, a little bit about the relay. Relay is another channel that's very much not understood. You know, everything almost is open there, but with this exception of the physically degraded channel that satisfies this constraint here. And in that case, the Y, the output, is essentially a degradation of the relay signal here. And then we can have an expression, this is in Culver's book, by the way, it's the supremum over all possible joint of x1 and x1 of the minimum of these 2 mutual informations. Wrapping up, the fronts that we have, there is a lot of work now being done in joint source and channel coding, even though there is the separation theorem that Shannon had. It also says that you know, you can achieve the rates, but doesn't say anything about the complexity. And very often when you do joint source and channel coding, the complexity can be extremely smaller than the separate complexities. Okay, coding for channels with side information. You know, distributed source coding, when you try to divide the effort of, say, sending an image through from a cell phone, transferring some of that effort to the decoder. You know, that would be an interesting, because the decoder lies on a Earth station with all the computers available and so forth. Network strategies, merging of network coding with multi-user information theory. That's something that would be interesting to see, using these building blocks of multiple access channel, broadcast channel, interference channel, and relay channel. In the applications usually worked with network coding, computer forward, and all these other strategies. Thank you very much. So that's it in a nutshell. Questions? In a nutshell? Yeah.
Maybe we are calculating the capacity with maximization over P. I was wondering if there is a theorem that says that we can always change any compressed source to the desired distribution P without adding extra resources.
I'm not aware. I would have to think about it. But you know, regarding the computation of the capacity, there is actually an algorithm that was distributed by people in different, at about the same time, but in different places. Arimoto and Blayhood found these iterative schemes that give you the optimal distribution. And it's an optimization. It's a compact, an optimization over a compact set of a concave function. So it always achieves a maximum.
Can we have any distribution on this source?
For the channel coding. For the channel coding, we assume that the source is uniform. No, you just want to send information over the set of messages uniformly distributed. Okay, so if you have some different distribution, that's probably going to make it easier for you, because that's the maximum information that's coming out of the source when you have uniform distribution over the message set. Okay. More questions? Thank you very much. Now we have the. I applaud you too for staying.